Hey everybody, welcome back. We're starting chapter 5. This is on nuclear chemistry. Nuclear chemistry is actually really important because of two reasons. One, nuclear power plants. They absolutely provide electricity for a lot of people. And two, nuclear medicine. We'll definitely talk about the nuclear medicine piece later on in the chapter. First, we're going to introduce radioactivity and talk about some of the different types of radiation. Radioactivity comes from unstable nuclei. I'll highlight here to show you some of the things you need to pay attention to. Radioactivity is found in carbon and hydrogen, as well as elements with an atomic number of 20 or higher. In these unstable nuclei, the nuclear forces cannot offset the repulsions between the protons. Remember that protons are positively charged. And yes, there are neutrons also in the nucleus, but all of those protons are packed in tight. Those protons are repelling each other because, well, they have the same charge, and like repels like. When a nucleus becomes unstable, it means that the nuclear forces that are holding it together can't offset the repulsions between all those protons in the nucleus. Radioactivity comes from small particles of energy called radiation. And that radiation is emitted so that the nucleus becomes more stable. We've got three forms that we're going to talk about. We got the particles, alpha and beta. We've got positrons, and we've got pure energy. A radioisotope is an isotope of an element that emits radiation. You can have multiple isotopes of an element that are radioisotopes, and you always want to include the mass number in the name. We have an example here for iodine 131, and that isotope is used to diagnose and treat thyroid disorders. The mass number is 131, and the atomic number is 53. What's shown below in this box is what's called atomic notation, where you have the symbol of the element, and then you've got the mass number on the top left, and the atomic number underneath. This table gives some examples of stable and radioactive isotopes of some elements. So we've got magnesium, iodine, and uranium. Stable isotopes, radioactive isotopes. Uranium has no stable isotopes, but it absolutely has radioactive isotopes. Magnesium and iodine, on the other hand, do have stable isotopes, but they also have radioactive isotopes. Let's look at the types of radiation. We've got alpha particles, which you will need to know this. You'll need to recognize the symbols for these. So alpha particles, it's a helium nucleus. Okay, so helium has a mass number of 4, which means it's got 2 protons and 2 neutrons. And the atomic number is 2 protons. We've got beta particles, which are just high energy electrons. And you'll need to know the symbol for that. Positrons, which a positron is essentially like a positive electron. And then there's pure energy rays, and those are gamma rays. This table will be very helpful because it summarizes some of the different types of radiation, and it includes protons and neutrons because those particles can also be emitted as part of radiation. I'd recommend putting this in your notebook because it will help you recognize the symbols and understand what they mean. Like I said, you'll need to know these for the exam. You will not be provided with this table. Radiation absolutely has biological effects. When ionizing radiation encounters molecules, it will knock away the electrons in molecules like water, and it's going to form unstable ions. Those unstable ions can do chemistry in the body, and they can cause undesirable chemical reactions to occur. Because of this, radiation can damage really pretty much any part of your body, right? But the cells that are most sensitive to radiation are the ones that rapidly divide. So we're talking bone marrow, skin, reproductive organs, your hair. All of these things are really affected by radiation. And if you affect certain things like the bone marrow and skin, you can cause cancer. The different types of radiation have varying distances that they can penetrate the body. So the alpha particles will pretty much be stopped by clothing. Okay, they're not going to go through your body. Beta particles will penetrate a little bit further, and gamma will go straight through you. Because of this, you have to wear protection. Okay, radiation protection means that you have the proper equipment and protection when you're working with specific types of radiation. So for alpha particles, you just need paper, clothing, okay? Beta particles, a good lab coat and some gloves is enough to block those beta particles. But when you're dealing with gamma rays, you need something very dense like lead or concrete because those gamma rays will go straight through human flesh. If you're working in an environment where radioactive materials are present, ways that you can limit your exposure are simply by minimizing the amount of time you spend near that radioactive source and increasing the distance between you and that source. This table pretty much summarizes the properties of radiation and what shielding, what protective gear you need to protect yourself. So this again is another really good summary table that will help you understand how far these particles can travel, how far they can penetrate tissue, and the types of protective equipment you need. It'll also give you examples of sources of these different types of radiation. Now we can look at nuclear reactions. Nuclear equations, we're just talking about an unstable nucleus releasing radiation, and then we have some new products on the other end. We're going to learn how to balance these equations. Radioactive decay. That's the process where the nucleus breaks down by emitting radiation. We can represent that with a nuclear equation. Within this nuclear equation, you may see something like the mass number and atomic number changing, but the sum of the mass numbers and the atomic numbers are equal for the reactants and the products. What does that mean? Let's say that we have this element here that's radioactive. Remember, the mass number is at the top. The atomic number is underneath. When this element undergoes radioactive decay, it emits an alpha particle, which is just a particle of helium. Knowing that an alpha particle means helium and that the mass number of that is 4 and the atomic number is 2, you can take 251, subtract 4, and that gives you a new mass number of 247, which is what you see here. Likewise, since we know that the atomic number has to sum 98 on the product side, we take that 98 and subtract the 2 protons we know come from helium, and we get 96. The atomic number gives us the information to identify the new element that is formed. We're going to talk about some different types of decay, and we'll do examples of each. So alpha decay, which we just saw on the previous slide, occurs when you emit an alpha particle from a radioactive nucleus. You form a new nucleus with a mass number that is decreased by 4 and an atomic number that is decreased by 2. On the right, you see an example of this where we're starting with uranium and its mass number is 238, which means that it has 92 protons and 146 neutrons. When it emits an alpha particle, notice how the new mass number for this new element is 4 fewer. 238 minus 4 gives you 234. The atomic number is 92 minus 2, which is 90. That 90, you can go to the periodic table and look up what element that corresponds to. That corresponds to thorium. So you could put that symbol in, and we already know we emit this helium particle. That's an alpha particle. That's going to be the same exact way that we solve our sample problem for alpha emission. Complete the following nuclear equation for the decay of americium-241. Here's our equation. We've got americium, mass number on the top, atomic number on the bottom. We know that the mass number has to equal 241 for both the reactants, which are on the left-hand side of the arrow, and the products. Since we know that our new element will have a mass number that is decreased by 4, we can take that 241 and subtract 4. This accounts for the mass number of the emitted alpha particle. What you get when you subtract that is the new mass number for your new element. We're not done yet, though. We can't use the mass number to identify the element. We need to know the atomic number. On the reactant side, the atomic number is 95, which means there's 95 protons. We know that helium has 2 protons. That's its atomic number. So we subtract that and we get 93. This is the atomic number for the new element. Mass number up top, atomic number on the bottom. Then you look up the atomic number. So you go to your periodic table, you find the atomic number 93, and you write down the symbol associated with it. That is neptunium. So our answer is neptunium with the mass number of 237. Oh, excuse me. Look at that. I wrote an 8 instead of a 3. Sometimes. That's why you check your work. Instructors make mistakes too. So that atomic number is 93. So 237 for the mass number, 93 for the atomic number. And I'll write you a note here. Look up on periodic table. We'll continue to do sample problems. For most of these, we may save some for live lecture to make sure that you come to live lecture too. The next kind of decay we'll talk about is beta decay. For beta decay, the new mass number of the new nucleus remains the same. The atomic number increases by 1. So in our example that's to the right, we have radioactive carbon. This is carbon 14. When it emits a beta particle, notice how the new element still has the same mass number of 14, but the atomic number has increased by 1. We started with 6, now we're at 7. You look up 7 on the periodic table, and that gives you nitrogen for the identity of the new nucleus. Let's do one on our own. Write the balanced nuclear equation for the decay of potassium 42, a beta emitter. Beta emitter means that you're going to release a beta particle. And you need to know what a beta particle looks like. That's a beta particle. So far, the information that we're given in the problem, we know that we're going to make some new element when we release this beta particle. Notice that there's something missing from the potassium. We need to fill in what the atomic number is. You can do this simply by looking at the periodic table and finding potassium. When you do, you'll see its atomic number is 19. So if you don't see an atomic number in the problem, that's okay. You can just look it up on the periodic table. I'll abbreviate periodic table PT. Now we need to figure out what our new element is. And we said that for beta decay, the mass number is the same. The atomic number we're going to increase it by 1. And this is for our new element. Mass number stays the same, so we'll write 42. The atomic number, we're going to say that's 19 plus 1. You look up this atomic number. It will tell you the identity of the element. It's calcium. And to complete our problem, or our equation, this is the complete equation. We had to figure this part out. So don't forget, your periodic table is your friend. You can always identify an element if you know the atomic number. Next, we'll cover gamma radiation. This is the easiest one. With gamma radiation, energy is emitted from the unstable nucleus, and that energy is indicated by an M following the mass number. The mass number and atomic number of the new nucleus are the same, so the element does not change. All you do is add your symbol for gamma radiation. So notice the M here. That M shows that you're about to emit some energy from this unstable nucleus. And when you do that, you still have the same element, just less energy. So this is a summary of the types of radiation. We did not cover positron emitters. It's pretty much the same thing as a beta emitter, only instead of adding 1 to the atomic number, you subtract 1. We'll do this type of problem in class just to make sure that you get it. So don't worry, I got you. In live lecture, we'll cover it. Let's talk about how you produce radioactive isotopes. If you have a stable nucleus, you can convert it into a radioactive nucleus simply by bombarding it with small particles. This process is called transmutation. The example that we have below, we've got boron, which is not a non-radioactive isotope of boron. You bombard it with a helium particle, that's an alpha particle, and you create a new radioactive nucleus. You now have radioactive nitrogen, and you also have a neutron. Let's practice writing an equation. Here, you're always going to be told what you produce because you won't just know off the bat what you're making. But if you're told what you're producing, then you should be able to come up with the new element. So write a balanced nuclear equation for the bombardment of nickel 58 by a proton, which produces a radioactive isotope and an alpha particle. So we know part of what's made. That means that we can figure out the new mass number and the new atomic number for this new radioactive isotope. Let's start by writing out what we know. Our reactants are the nickel 58 and the proton. The products are a radioactive isotope that we don't know its identity and an alpha particle. Remember that when you see that element name, dash, and a number, that number is the mass number. You're told what a proton looks like. And we make some new radioactive isotope plus an alpha particle. You need to know what these particles are. We're missing one small piece of information. We don't have an atomic number. But that's not a problem because you should have your handy dandy periodic table. That's right. Fill it in from the periodic table. I'm a mom. I have kids. Don't judge me. You can always fill in the atomic number from the periodic table. Now we need to figure out what our total mass number is for the reactant side so that we can make that equal our product side. We've got the 58 from the nickel plus 1 from the proton. That means the mass number is 59 total for the reactant side. For the atomic number, you take the 28, which we figured out from the periodic table. You add 1 from the hydrogen, and that gives you 29. Since we know that these totals have to be the same on both sides, we can use subtraction to figure out the mass number and atomic number for our new radioactive isotope. We know the mass number of the alpha particle. That's 4. What we don't know is the mass number for our new element. We'll call that X. Subtract 4 from each side, and you get 55 for the new mass number. Let's put that up top. We'll do the same exact thing for the atomic number. And remember, we're doing this for the products. So 29 is equal to the atomic number from the alpha particle, which is 2, plus our unknown. We'll call that y. Subtract 2 from both sides. And 27 is equal to y. That's our atomic number. You look up that atomic number on the periodic table. That will tell you the identity of the element. The element with an atomic number of 27 is cobalt. So to write out our final answer, I'm going to block off some space here. The balanced nuclear equation is, we take our nickel, we bombard it with a proton, and we generate radioactive cobalt plus an alpha particle. With practice, these problems will become very simple. You have to understand the difference between the mass number and the atomic number, which was talked about in Chapter 4. So if those two concepts are a little fuzzy, you don't really remember them, you need to go back to Chapter 4 and understand what the mass number is and the atomic number is. Then you can jump back to Chapter 5 and it'll be a piece of cake. So we've covered the different types of radioactive decay. Now we'll talk about how we can measure radiation. So here you see a picture of workers at Fukushima Daiichi, the nuclear power plant in Japan. Their radiation levels are being measured in this picture. And I remember this. I remember when that incident happened. It was in 2011. And I was a real adult then. It's kind of crazy to still see this happened a decade ago, and we're still seeing the effects of it now. So radiation is quite serious, and it should be taken seriously. If you ever do work with radioisotopes, you end up working in a nuclear power plant, or anything to do with radiation, please take it seriously, because radiation sickness is very real, very bad, so treat it with respect. With that said, let's keep going. We'll describe how radiation is detected, and how it's measured. A Geiger counter is a very common instrument whenever you're dealing with radiation. If you work in a research lab where you use radioactive isotopes, you'll absolutely have a Geiger counter. Geiger counters detect alpha particles, beta particles, and gamma rays. And these ions that are produced by radiation create an electrical current that can be detected. So that's how they work. There are several different units that can be used to measure radiation and radiation activity. We have the Curie, which is named for Marie Curie. We have the Becquerel, which is the SI unit. Always know which unit is the SI unit. We've got the RAD, which is the radiation absorbed dose, and the REM, radiation equivalent in humans. We'll be talking about all of these, and we'll do a little bit of calculations here and there within this lecture video, but we'll also do some practice problems in the live lecture to make sure that you understand how to convert between these. The REM, the radiation equivalent in humans, measures alpha particles which don't penetrate the skin. But if they do enter the body, they will do extensive damage. REMs also measure high energy radiation, which causes more damage than alpha or beta particles. Okay? This type of radiation will travel into your tissue. And then gamma rays are damaging simply because they can travel a long way through the tissue. So we need to use REMS to talk about the radiation equivalent in humans, so we can talk about what are you experiencing. To determine the equivalent dose, or the REM dose, you take the absorbed dose, which is the rad, and multiply it by a factor that adjusts for the biological damage caused by that particular form of radiation. So depending on the particle, that factor will be big or small. You'll want to be familiar with this equation. It'll be provided for you on your equation sheet, so you don't have to memorize it, but you do need to know what each piece means. So to calculate the REM, the biological damage, you take your absorbed dose and you multiply by the factor that goes along with the type of radiation you're interested in. For beta and gamma radiation, that factor is 1. High energy protons and neutrons, it's about 10. And for alpha particles, it's 20. But remember, with alpha particles, you're not really absorbing anything because they don't really penetrate through clothing. Oftentimes, the measurement for an equivalent dose will be in millirems, and this is the abbreviation for millirems. So don't forget those metric prefixes, because you'll see them time and time again whenever we do math. Here's an equality that will be helpful for you. It will not be provided because you should know that 1 rem, you should know milli. Milli is 1,000, okay? So milli would be 1,000 times, or 1,000 times smaller than 1 rem. The SI unit we talked about is the sievert. This is another equality. You do not need to memorize this one. 1 sievert is equal to 100 rem. You do not need to memorize it. All of the relationships in this third or fourth column here, these are all equalities that you will not need to memorize. So let's talk about measuring radiation damage with a little bit of a real situation. So foodborne illnesses are caused by bacteria like Salmonella, Listeria, and E. coli. And they've become major health concerns in the U.S. I feel like every few months there's a recall for something because there's Salmonella detected or E. coli detected on your spinach or your romaine lettuce or something like that. The FDA has approved radiation as a treatment for foods. So foods will pass through a series of racks, and the gamma rays pass through the food and kill the bacteria. So that's one way that you can treat food before you put it on the shelf. And this includes produce and all the things. So you put that food through radiation treatment, and then you can ship it off to grocery stores and wherever else it's supposed to go. So radiation is used in a lot of areas that you would not think it would be used. So right now, tomatoes, blueberries, strawberries, and mushrooms are allowed to be irradiated when they're harvested so that they can actually, be on your shelf for more than a day or two. If you didn't do that, then they'd become moldy and nasty pretty quick because of all the bacteria and things that can kind of get in there, and it's kind of gross, to be honest. When you see this symbol on your food, it means that it's been irradiated. People who work in radiation laboratories, pilots, flight attendants, because you're exposed to radiation every time you fly, you have to wear a dosimeter. And that shows how much radiation you've been exposed to. So it will change colors based on how much radiation it detects. And since it's hanging right on your clothing, you clip it to a pocket or something like that of your lab coat, or if you're a flight attendant or a pilot, you clip it to like a shirt pocket or something like that. It will show a color based on how much radiation you've been exposed to cumulatively. And that helps to keep track of, okay, you need to take a break because there are certain rules for how much radiation you can be exposed to in one given moment and how much you can be exposed to over a certain length of time. So this little chart shows you the annual radiation received by a person in the U.S. It talks about natural sources like from the food and water and air and stuff like that. Medical exposure, so dental x-rays if they look at your teeth, chest x-ray, mammograms, all kinds of things. And then there's nuclear power plants, your TV, air travel. All of these things are exposing you to radiation whether you know it or not. Some of the naturally occurring isotopes that occur in food are potassium-40. So anything that's potassium rich, we always tout bananas as being potassium rich, which, they do have a decent amount. But potatoes have a lot of potassium. So any food that's rich in potassium, you're going to have, more radioisotopes of potassium, potassium-40. You also experience cosmic radiation from the sun. So every day, everywhere, we're exposed to radiation, just very, very low levels. But if you receive a very large dose of radiation at one time, it will have a major effect on the body, and that's called radiation sickness. And if you're exposed to a high enough level of radiation, you can actually die from radiation sickness. The amount of radiation to the whole body that if 50% of the people receive it die, or it's lethal for them, that's called the LD50. Okay, that's lethal dose for 1/2 of the population. We can't take very much in the way of radiation. 5 sieverts, and that is the LD50. However, insects and bacterium, they can take a lot of radiation. So, yeah, keep that in mind. It's pretty crazy. So be careful is the summary of all this, talking about radiation and radiation exposure, radiation sickness, not to scare you, but just to be cautious, be mindful of your exposure, especially if you're someone who likes to fly a lot. So we can do some more calculations with radioisotopes. Radioisotopes eventually will decay. And when they decay, they're no longer a radioisotope, right? They change their identity. So we can talk about the half-life of a radioisotope. Given the half-life of a radioisotope, we can calculate the amount of radioisotope remaining after one or more half-lives. But what is a half-life? The half-life of a radioisotope is simply the amount of time for the radiation level to decrease to 1/2 of the original value. So here we've got iodine 131. Let's say that we're starting with 20 milligrams of this radioactive isotope. Its half-life is 8 days. So if you started with 20 milligrams, 8 days later, you will only have 10 milligrams left. If you wait an additional 8 days for a total of 16 days, that's 2 half-lives. So you now have 5 milligrams, half of what you had after the first half-life. And if you wait an additional 8 days for a total of 24 days, that's 3 half-lives. So you now have 2.5 milligrams of your radioactive isotope. A decay curve can show that 1 half-life occurs every 8 days for iodine 131. If you keep track of the time on the x-axis and the amount of the radioisotope that you have on the y-axis, you can plot this every day or every, hour or whatever you think is appropriate, and you can calculate the half-life. And once you get to the point where you have half of the amount of material you started with, that's your half-life. This table has the half-lives of some radioactive isotopes. We've got naturally occurring ones like carbon-14, potassium-40, and then some medically relevant ones. You'll see the iodine 131 down here. We'll also probably talk about the technetium 99. But let's do a calculation. We've got the radioisotope strontium 90, and it has a fairly long half-life, 38.1 years. If a sample contains 36 milligrams of strontium 90, how many milligrams will remain after 152.4 years? Let's highlight the information that is relevant. We've got a half-life of 38.1 years. We know that we're starting with 36.0 milligrams of our sample. And we need to know how many milligrams after 152.4 years have passed. One half-life, which I'll abbreviate HL, is equal to 38.1 years. That looks suspiciously like an equality. Because it is. If we have an equality, we can write conversion factors. One half-life over 38.1 years. And 38.1 years over 1 half-life. Now we can take the time that's elapsed, which is the 152.4 years, and figure out how many half-lives. So that's the first thing that we're doing to solve this problem. Let's calculate the number of half-lives in 152.4 years. We have to use the conversion factor that will cancel out years. Years is already in the numerator, so we need years to be in the denominator. When we do this math, you will take 152.4 and divide by 38.1. When you do that, you'll get 4 half-lives. Now we figure out how much sample will remain after 4 half-lives. This is where we're starting. If we do 1 half-life, then we divide by 2, and we get 18 milligrams. For the second half-life, we divide that 18 by 2. For the third half-life, we divide 9 by 2 to get 4.5. And notice that I'm keeping 3 significant figures the entire way, because that's what we started with our sample amount. 36.0 milligrams has 3 sig figs. For our final half-life, half-life number 4, you divide 4.50 by 2. And that is our final answer. There are lots of medical applications that use radioactivity. We're going to describe the use of radioisotopes in medicine. Ideally, you want to use radioisotopes with a short half-life when it comes to nuclear medicine. And the reason is the cells in your body will not differentiate between non-radioactive atoms and radioactive atoms. And once your body incorporates these atoms into your body, into proteins and other structures in the body, they're going to emit radiation. They emit radiation, which is a good thing if you're trying to detect and look at, an organ or something in the body. But you don't want that to continue going on for years and years and years, because radiation is bad for the body long term. So the short half-lives for nuclear medicine is great because the radioisotopes will decay within a few months of use. So you have a smaller and smaller and smaller amount, and within a few months, it's gone. So you're not doing too much damage to the body. This table has all these different types of radioisotopes, what their half-lives are, and medical applications. This table may be helpful to you when you're doing your homework. You may need to use a half-life from here, or you may need to look at some of the different ways in which these isotopes are used. I'm not going to read it to you, but just take note that table 5.8 has medical applications of radioisotopes. After that isotope is ingested by the patient, a scanner is going to move slowly over that part of the body where the radioisotope is absorbed. So we talked about iodine 131. That is used to detect issues in the thyroid. So they're going to scan your neck. Okay. The radiologist determines the level and location of the radioactivity emitted by the radioisotope. If there's gamma rays emitted, then you can expose a photographic plate and produce a scan of the organ. Here's an example of a scan showing the iodine 131 in the thyroid. What this is essentially a heat map. So the more red something is, the more you're seeing that radioactive isotope emit. So you're seeing the greens and the yellows and the reds. That's where you're seeing your isotope. The blue, you're not really seeing much. Positron emitters, they have the ones with short half-lives, can be used to study brain function, metabolism, and blood flow. And here's some examples of the different positron emitters that can be used. You combine that with detection by computers, you can make a 3D image of the organ. So it's really handy. PET scans, you can scan the brain, and you can look at a disease state versus a normal state. You can detect Alzheimer's disease. Then there's computed tomography, or CT scan. You can look at the brain, lungs, the heart. A computer monitors the absorption of all these X-ray beams, and you can direct it at the brain or whatever other organ in successive layers, so different penetration. And the differences in absorption based on the tissue densities can provide a map of the brain. With that, you can look at, the different structures of the brain, and you can identify tumors, for example. Then we've got MRIs, so magnetic resonance imaging. You don't actually use nuclear radiation here, and it's one of the least invasive imaging methods available. You don't have to take any kind of medication beforehand. So with all of these other ones, if you have to, identify where a radioisotope is in the body, you have to ingest a medication that has that radioisotope, wait a certain amount of time, then you have to go to your appointment within a certain window, and it's a whole big mess. MRIs are nice because you don't have to take anything, it's non-invasive, and it's just based on the absorption of energy when protons in hydrogen atoms are excited by a strong magnetic field. Remember, we're mainly water, which has a lot of hydrogen, and there's a lot of hydrogen in our bodies, so this works pretty well. The energy absorbed is converted to color images of the body, so you can see all the organs and things, and you can diagnose a lot of issues. This is an example of an image of the heart and the lungs. There's a process called brachytherapy, which is also called seed implantation. That's an internal form of radiation. And it's literally taking a piece of radioactive isotope, and implanting it. It's a treatment option for prostate cancer in males. So you can have permanent brachytherapy, where you implant 40 or more tiny little titanium capsules, which are also called seeds, hence seed implantation, in the malignant area, so the prostate area where you have the tumor. You can also use other radioactive isotopes like iodine-125, palladium-103, etc., and they decay by gamma radiation, or gamma emission, And that radiation will destroy the cancer cells around it. And the benefit here is that you've got minimal damage to adjacent normal cells. Temporary brachytherapy is also an option. You insert long needles that have an isotope that has a shorter half-life, right? Or you can just remove the needles after a few minutes. And you can repeat this treatment over and over every few days until the area that you're looking to remove cancer from is cancer-free. So that was a nice little foray into the medical side of things. Hopefully that helps to make understanding nuclear chemistry a little bit more interesting, just to see the real world applications. Now we're going to talk about nuclear fission and fusion. And this is also very relevant because of nuclear power plants, but also because this technology has been used to create bombs, right? World War II. So this is a history lesson along with making all of this very relevant. Nuclear fission. That's when you take a large nucleus like uranium-235 and you bombard it with a neutron and you make an unstable isotope. That isotope then splits into smaller nuclei and you make more neutrons. And those neutrons will then bombard more of the uranium-235 to create more unstable isotopes that will then release more neutrons, so on and so forth. You end up releasing a large amount of energy called atomic energy. This is a depiction of that very same reaction. So you bombard the uranium-235 with a neutron. That nucleus becomes unstable and it wants to release a lot of energy. That's what this little sunbeam is, sunburst. This is energy. You create two different elements and you release more neutrons. These neutrons can then go on and bombard more of that uranium-235. So it is a self-perpetuating reaction. This is also called a nuclear chain reaction because, again, those three neutrons that you produce can then go on and find three more atoms of uranium-235 to cause three more reactions to then release 9 more neutrons, so on and so forth. Nuclear fusion, on the other hand, occurs at really, really high temperatures. And fusion is just that. You're combining small nuclei into larger nuclei. This causes a very large release of energy. This is also the reaction that's going on in the sun and other stars in the solar system. So the energy from nuclear fusion is so great that it can get all the way to Earth, come on down to the surface, and heat us up. So when we say large amounts of energy, think really, really big. In a fusion reaction, what we're doing is producing a large amount of energy simply by taking hydrogen isotopes and combining them to form helium. This process is less wasteful than fission. But we don't know how to do fusion, y'all. Not like that. We don't know how to make the sun. Okay? So fission is what we're left with. This is a depiction of the nuclear fusion reaction that's going on in the sun. You've got two different isotopes of hydrogen, and they combine to make helium. You also release neutrons and a lot of energy. When they were making this slide, they forgot to put lots of. That's a scientific term. Lots of energy. Okay? This is the concept map for Chapter 5. It has a lot of the terms that we talked about, and it shows you how they're all related. As usual, I'm not going to talk through this, but if you want to use this to make sure that you understand what concepts you're responsible for in Chapter 5, that you can identify all of the vocabulary you need to know, that you can put words to those vocabulary words and define them, use them, etc., go for the gold. I always encourage you to use the skills and use the things that work best for you to make sure that the information you just received is actually retained. With that, thanks for watching. Hope it was helpful to you. Make sure that you tune in to live lecture for practice problems, especially for those nuclear equations and for the positron emission. So come to live lecture for that, and also for details regarding assignments and exams. As always, be safe, and we'll see you soon.